This is the second part of the Hopfield Network. In this video, we'll look at the energy function of the Hopfield Network. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. In the last video, we stored simple image patterns in a Hopfield network and reconstructed corrupted images using the activation values of each neuron in the network. In this video, we will reconstruct the corrupted images using the energy function of the Hopfield network. First, let's understand the energy function through the Ising model in physics. And then let's apply this to the Hopfield network. Now let's take a quick look at the Ising model. The Ising model, or Lenz-Ising model, named after the physicists Ernst Ising and Wilhelm Lenz, is a mathematical model of ferromagnetism in statistical mechanics. The model consists of discrete variables that represent magnetic dipole moments of atomic spins that can be in one of two states, +1 or -1. Consider a physical system, a magnet, represented as a two-dimensional lattice configuration in the Ising model. It's a huge square lattice of sites, where each site can be in one of two states, +1 or -1. Each of the sites is an atom with spin. Each spin acts like a tiny magnet with its own small magnetic moment. The red up arrow represents spin up, +1, and the blue down arrow represents spin down, -1. When the individual spins are not aligned in a regular and coherent way, like this, the magnetism will be weak. This is because the collective effect is diminished, resulting in a weaker overall magnetic response. Conversely, when the individual spins are aligned in a regular way, like this, the collective effect is greater, resulting in a stronger magnetic force. A function representing the energy of every single possible configuration of the spins in the magnet can be defined as follows. SI represents the individual spin at each lattice site. This notation indicates that sites I and J are nearest neighbors. Jij represents the interaction strength between the two spins, Si and Sj. Mu represents the magnetic moment. And Hj represents the external magnetic field interacting with Sj, which can be interpreted as a bias. When Si and Sj have the same sign, either aligned, the energy is smaller, but when they are not aligned, the energy is larger. Therefore, this magnet has high energy, and this one has low energy. Let's consider the four neighbors around the spin Sa. We assume that J is 1 and H is 0. By this formula, the energy of this configuration is calculated as follows. The spin Sa is +1, and all four adjacent spins are also +1. So the energy of this configuration is -4. If the spin Sa is flipped to -1, the energy becomes 4, which is higher than before. Delta E, the energy difference before and after the Sa flips, is 8, which is greater than 0. Systems in nature tend to move toward lower energy and higher entropy. Lower energy is preferred because it makes the system more stable in nature. Therefore, the spin Sa does not flip since this configuration is already stable. Conversely, if the spin of this site in this configuration is -1, the spin tends to flip to the opposite state. We could define a probability distribution, which is a function that returns a probability for each possible state of the system. This is called the Boltzmann distribution. Here K is a constant, T is temperature, and Z is a normalizing factor. This is a probability distribution, but it has the property that all states with the same energy are equally likely, and states with lower energies are exponentially more probable than states with higher energies. This configuration, consisting of 5 particles, has a total of 32 possible states. If this configuration has the lowest energy among these, then this probability is highest. There is one more variable to consider in this system: temperature. The lower the temperature, the more effectively the spins tend to align. When T is low, this value increases, making P very sensitive to energy changes, i.e. P decreases rapidly even with a small increase in energy. Conversely, when T is high, P is insensitive to energy changes. So even if the energy increases significantly, P decreases slightly. Therefore, it is somewhat acceptable for this configuration to move to higher energy states depending on T. The Ising model can be simulated by this algorithm. When the energy decreases, flip the spin. Otherwise, flip the spin with this probability. For more details on the simulation, please refer to this document. Now, let's briefly implement a simulation of the two-dimensional Ising model. Let's create a two-dimensional lattice like this, where each spin is randomly up or down. The lattice size is 100 by 100. We set KT of the Boltzmann distribution to 2.2, which is the critical temperature. Below the critical temperature, the spins are well aligned, but above the critical temperature, the spins are not well aligned. Next, we write a function that computes the total energy of this system. We use this formula to compute the energy. Let us assume the coupling strength J is 1, and the external magnetic field H is 0. Add the spins of all sites adjacent to a given site, and compute the energy. Compute the energy at all sites and accumulate them to compute the total energy. I used Numba's just-in-time compiler to speed up the execution time of the code. Next, we update the states of each spin to stabilize the system. This lowers the energy of the system. We randomly choose a site on the lattice, and then we compute the sum of the spins around that site. Next, we compute the energy difference before and after flipping the spin of a randomly chosen lattice site. If the energy decreases, the spin flips. If the energy increases, the spin does not flip, but it may flip depending on the temperature. That is, depending on this probability, the spin may or may not flip. Repeat this process. Call this function repeatedly to change the spins on the lattice. And measure the energy. Display the changed configuration of the spins during iteration. Finally, plot the changes in energy. Let's check the results. The results when KT is 2.2 are as follows. This is a lattice of size 100 by 100. At initial state, each spin is up or down randomly. The yellow-colored dots are representation of up states, whereas the blue ones are down states. As the system evolves, the spins are aligned in the same direction, and the magnetism becomes stronger and stronger until it finally becomes a magnet. As the iterations progress, the energy of this system decreases like this. The results when KT is 1.0, which is lower than the critical temperature, are as follows. The spins are better aligned, and the magnetism becomes much stronger. The energy decreases further. The results when KT is 3.0, which is higher than the critical temperature, are as follows. The spins are not aligned, and no magnetism is generated. Energy does not decrease either. Let's run this code. We got the following results. Now let's apply this energy function to the Hopfield network. As we did in the previous videos, we store these image patterns in a Hopfield network. This process is the same as what we looked at before, so I will skip the explanation. Next, let's retrieve the image patterns stored in the Hopfield network using the energy function. To simplify notation, we will denote the bipolar state as S. The energy function of the Hopfield network is defined as follows. In the energy function of the Ising model, when the external magnetic field H is 0 and the coupling strength J is W, it becomes the energy function of the Hopfield network. When the spins Si and Sj are aligned, increases and the energy decreases. Now let's use the trained Hopfield network to reconstruct the corrupted pattern. This test pattern is a pattern where the second state of the first input pattern is corrupted. Let's update the state of each neuron in this random order. First, we update the state of neuron 2. Flip the second spin. We use this formula to compute the energy before and after the flip. The energy before the flip is -12, and the energy after the flip is -32. The energy after the flip is smaller. So we flip the second spin. Next, we update the state of neuron 3. The second spin has already been flipped in the previous step. This time we flip the third spin and compute the energies. The energy has increased, so we don't flip the third spin. Update all other states in this way. The corrupted image is then reconstructed. The Boltzmann distribution is not used in Hopfield network. Finally, let's implement this in code. The input patterns are as follows. Convert them into bipolar states. Compute the weight matrix. These are the corrupted images that are test patterns. Convert them into bipolar states. As we saw in the examples on the previous page, we use the energy function to update each state of the corrupted images. Check the results. Each corrupted image was reconstructed as follows. You can see that they have been restored to their original image patterns. Energy has also decreased. Let's run this code. We got the following results. In this video, we look at the Ising model and energy function and use them to implement a Hopfield network. In the next video, we will look at the pseudo-inverse learning rule of the Hopfield network.